Oh my goodness. This is the last lesson video of the year. Hey, pre-calc, it's your birthday. Hey, pre-calc, it's your birthday. You're going to learn it like it's your birthday. All right, I'm done. I'm completely done. I can't even get more corny now. Okay, so let's just get it done. All right, so we've been doing this now for the past few lessons, sigma notation. This is not new, but let's devote a lesson to deciding how to simplify sigma notation, or even expand it or solve it in an easier way. All right, so before putting it in any notation or using any formulas, ask yourself this: does the sigma notation represent a pattern that's geometric, or a pattern that's arithmetic, or a pattern that might be neither? All right, so I made a little side note here. Pattern is arithmetic. When you look at it, if you see no exponents whatsoever, no exponents, you got yourself an arithmetic pattern. It's geometric if you see exponents, but I'm going to write this: variables only in the exponents. Slight distinction, but I'll show you in just a second with that. All right, it's neither if it's basically if it's anything else. You got anything else, if you see numerical exponents, or maybe if the lead term has a variable as well. All right, I'm just going to write anything else. So let's get to it. We're going to fly through this like Superman. All right, here we go. Looking at number one, before I even go anywhere, I just see this term right here. Boom, it's a base raised to a variable exponent. That's geometric. Remember, whatever the base is, that is what the term is. Now, a way that you can either further help yourself, and I'm going to say this absolutely, as clearly as I can, just find the first three terms. Literally just plug in the first number, then the next integer, then the next integer, and get three terms, and then look at the pattern of three numbers and see if it's geometric or arithmetic. That's always a way that you can go. And in this case, 3, 9, 27, yes, you're multiplying by 3, r equals 3. So that means you could use the geometric sum formula, which is right here. The first term is 3. Boop. All right. The r value is also 3. And you're finding the sum of 17 terms. Remember, one thing you could do: n equals the top term minus the bottom term plus 1. So that equals 17 right there. So make sure that when dealing with sigma notation and you're finding the number of terms n, you take the top minus the bottom and then make sure you add 1. Okay, and just plug all that into your calculator: 193,710,243. Boom. Okay, you've done this enough times. I'm not going to go through the calculation with you. All right, let's check this one out. Ooh, this one certainly looks geometric right here, doesn't it? Something raised to a variable exponent, but there's another variable lurking in the problem. It's in the denominator. Or if you wanted to change this to multiplication, it would be 1 divided by k plus 1 times -2 to the k power. Bottom line, in order to be geometric, you can have variables only up in the exponents. This definitely has a variable as an exponent, but it also has a variable as what would be. Think about what geometric means. Geometric is what? A sub 1 times r raised to the n minus 1. This first term is a constant. It's not a variable. So because, and by the way, how could you prove that? Plug in 1, plug in 2, then plug in 3. Get 3 terms: -1, positive 4/3, -2. All right, the r value is not constant, so it's neither. So what is the only way to find this? Glade commercial. Plug it in, plug it in. When it is neither arithmetic nor geometric, you don't have a formula, just plug it in and go. So your good news, you're only going from 1 to 5, so plug in 1, 2, 3, then find the fourth term, then find the fifth term. I mean, honestly, you could use your calculator if you want to, then do math, enter, enter, and get -19/5. Honestly, yes, I'm not going to make it. You're in pre-calc A. I'm not going to make you add and get common denominators. You could do -1 plus 4 divided by 3, -2 plus 16 divided by 5, plus -32/6. Hit enter. It's going to give you a decimal on your calculator. Hit math, enter, enter, and it will give you the reduced improper fraction. Done. Okay. Number 3, absolutely no exponents. Arithmetic. What's up? It's arithmetic. And how could you find out what D is the common difference? Well, you don't necessarily need to find it, but yes, you do. All right, why? Because you need to find the first term, and you also need to find the 20th term. And how do you find the 20th term? You do a little side work. That's how. To find the 20th term, you do 5 plus 3 times 19. This is where, oh, by the way, finding D is where finding the first 3 terms of the sequence really helps you visually. You can see that D equals 3 here. So then D equals 3, multiply 3 times 19, you get the 20th term as 62. Then it's 20 divided by 2, which is 10. And then the first term is 5. The 20th term is 62. And Bob's your uncle. You get 670 right there. Okay. So there is number 3. Number 4. Ooh, this looks really weird, right? But the only place where I see variables are up in the exponents. So what you can do to prove to yourself that this is geometric is find the first 3 terms. Plug in 1, then plug in 2, then plug in 3. Evaluate. You get -6, -18, -54. Ooh, boy. It is geometric, and R is -18 divided by -6, which is +3. So now that we've determined it's geometric, let's use the geometric sum formula. All right, remember what n is. N equals 10 minus 1 plus 1, that equals 10. So the sum of the first 10 terms is the first term, -6, and then 1 minus r raised to the 10th power, 1 minus 3 to the 10th power divided by 1 minus 3. Calculator gives you -177,144. Oh yeah. Number 5, 4n. Hey, there's no variable. So no exponents there. It's arithmetic. How do you find D? Help yourself. Find the first few terms. 0. No, notice that 0 is the first term here. So 0, and then plus 4, plus 8, plus 12. So D is 4. So to find the sum, now hold on a second here. How do you find n? N equals 5 minus 0, but plus 1. So n equals 6. All right, so just to go through the formula here, it's going to be 6 over 2, and then it's going to be the first term. I'm going to write a sub f, the first term, plus a sub 5. So I guess I should be more specific. It's going to be a sub 0 plus a sub 5. All right, so the first term is 0. How do you find, oops, I apologize. Let me get my eraser out. Make a boo-boo. This should be a sub 6. Apologies. No! Ay, 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 ay. Okay. It's going to be, it's weird to say, but it's, how do you find the last term? You find the last term by plugging in a sub 5, even though there's 6 terms in between it. So let's go through here. You know what? Let's just call this a brain fart on my account. I'm just going to go and just say, just going to call this in general. Ready? Oh my goodness, you can tell I can't get it through on the last lesson right here. My gosh, I'm going to call this the first, and I'm going to call this the last. It's actually how I do it in my class too. The first term is a sub 0. The last term, plug in, boom, you get 20. You get your final term of 60 right there. Okay. Done and done. All right. So now we move along with this. Oh, we're getting all trigonometric on you right here. Okay, so cosine of n times pi. So first off, where did this 1 come from? That's the cosine of 0. Okay, and just going through right here, you got 0, pi over 2, pi, 3 pi over 2, and you got 1 comma 0. Write your unit circle if it helps. 0 comma 1, negative 1 comma 0, and 0 comma negative 1. Go around and around and around and around. Okay, and so you could find the cosine of 0. Oh, and by the way, r equals 1 no matter where you are. Remember that cosine is x over r. So at 0 radians, cosine of 0 is 1 over 1. Boom. And then plug in 1, cosine of 1 pi. Cosine of pi is negative 1 over 1. Then 2 pi. So basically you're sitting only on the x-axis. You're toggling from 0 to pi, then to 2 pi, and 3 pi, and so forth. So you don't need the pi over 2 or 3 pi over 2. But then we're finding the first 3 terms right here. Yeah, I noticed that there's no exponents, but this is geometric. I should say, I'm going to put it up top here. Okay, there are trig exceptions. There doesn't need to be exponents when dealing with trig. Oops, sorry. Okay, so then r is negative 1, because negative 1 divided by 1 is negative 1. 1 divided by negative 1 is negative 1. So it's geometric r is negative 1, definitely. How many terms are there? 51. 50 minus 0 plus 1. Got 51 terms. Plug it all in. All right, 1 minus negative 1 is positive 2. Negative 1 to the 51st power, that's an odd power, so this is negative 1. So 1 minus negative 1 is positive 1 plus 1, which is 2. 2 divided by 2 is 1. All right. To finish this thing up here, what if you have a double sum or a nested set of summation notations? You work your way from the inside out. I'll write that, inside out. So deal with the inner sum first. So it's the sum as j goes from 1 to 2 of 2k plus j. Now, I notice there's a k there, but we'll deal with that in a moment. There's the k. All right, so we're plugging in 1 for j. Then we're plugging in 2 for j. And we could, and I know that Miss Middleton wrote x right there. This is supposed to be a k. That's a k. All right, 2k plus 2k is 4k plus 3. So now we're dealing with the outer sum. The sum as k goes from 1 to 3. That's a 3 right there. 4k plus 3. So plug in 1, plug in 2, plug in 3 for k. Get 3 values, evaluate, and you got your final answer. So double sum, not that bad. Deal with the inner sum first, then the outer sum. All right, so the sum as k goes from 1 to 3 of j raised to the power of k. So plugging in k first. So it's going to be 1 k to the first, or j to the first, then j squared, then j to the third. You've just done the inner sum. Now it's the sum as j goes from 1 to 4 of this term. So that's exactly what Mrs. Middleton did. 1, 1 squared, 1 to the third, 2, 2 squared, 2 to the third, 3, 3 squared, 3 to the third, 4, 4 squared, 4 to the third. Find 4 values, evaluate, get your overall sum. So while a double sum might look intimidating, it's not. You could even do triple sums. Work your way from the inside out. Last but not least, number 9. Oof, this looks tough. Sum as n goes from 1 to 1,000 of 3n minus the sum as n goes from 1 to 999 of 3n. Well, let's start with this sum right here. This is this. So it's going to be 3 times 1, 3 times 2, 3 times 3, all the way up to 3 times 1,000. And then minus this term right here. And you get what I'm, boy. Yeah, I messed that one up. Anyway, you get what I'm talking about. This goes from 3 times 1, 3 times 2, 3 times 3, only up to 3 times 999. Now, if I get rid of that bracket, that's going to be minus 3, minus 6, minus 9, minus all the way up to 3 times 999. So what's going to happen here? This 3 is going to cancel out with this 3. This 6 is going to cancel out with this 6. This 9 cancels out with this 9. All the way up to 3 times 999. What's the only term left standing? Well, it's the last term from the first set, the 3 times 1,000. That's what goes right there. That's the only one that's left standing because everything else is going to cancel out. So 3 times 1,000 is 3,000. That's all that you're left with. Everybody, I'm going to give you a hand. Congratulations. You've completed the lessons of this course. Do this homework. Get credit. See ya.